Welcome to a video on solving absolute value inequalities. In this video, we'll look at the between solutions by understanding absolute value of x is less than or equal to a and absolute value of x is less than a. This is where a represents any real number. Let's get started. Let's look at absolute value inequalities, the between case. For any real number x, with a greater than or equal to 0, if the inequality is the absolute value of x is less than or equal to a, then the solution is x is greater than or equal to negative a, and x is less than or equal to a. In other words, x is between negative a and a, including the endpoints. If the inequality is the absolute value of x is strictly less than a, then the solution is x is greater than negative a and x is less than a. In other words, x is between negative a and a, excluding the endpoints. While these inequalities look and sound very similar, there is one subtle difference. The first inequality is less than or equal to, and it includes the endpoints negative a and a. The second inequality is strictly less than, and the solution set excludes negative a and a. It is possible that some of these types of problems have no solution. If you get absolute value of x is less than or equal to a negative number, or absolute value of x is strictly less than a negative number, there is no solution because an absolute value can never be negative. For example, the problem absolute value of x is less than or equal to negative 5 has no solution since absolute value of x cannot be less than or equal to a negative number. Before we look at how to solve these types of problems, let's make sure we understand the solution set. A solution to an absolute value inequality is usually not just one number. The solution set contains every value of x that makes the inequality true, and this typically includes infinite many solutions. In math, whenever the solution includes infinite many solutions, there is a variety of ways we can express the solution set. For these problems, we will express the solution set using inequality notation, using interval notation. Remember that we use square brackets for the regular inequalities that include the equal bar. We use round parentheses for strict inequalities like strictly less than, strictly greater than, and for positive and negative infinity. We also represent the solution set in graph form. This is where we shade all included values. For these problems, we use closed dots to represent that the endpoint is included. These coordinate with the regular inequalities that include the equal bar below. And we use open dots to represent exclusion of the endpoints. This is when we have strict inequalities like less than or greater than. Let's look at the example absolute value of x is less than or equal to 7. We could express the solution set in inequality notation by writing x is greater than or equal to negative 7, but less than or equal to 7. In interval notation, we would write this as the interval from negative 7 to 7, using square brackets for both negative 7 and 7 to represent that they are included in the solution set. Graphically, we would use a solid dot at negative 7 and a solid dot at 7 to represent these values are included, and we would shade everything between negative 7 and 7 to represent the solution set. Now let's learn the steps to solving absolute value inequalities. As we learn the steps, let's solve the inequality 3 times the absolute value of x minus 1 is less than or equal to 8. The first thing we need to do is to isolate the absolute value expression. We want to get the inequality into the form absolute value of x is less than or equal to a, or absolute value of x is less than a. The first thing that we need to do for this problem is to isolate the absolute value of x. So let's add 1 to both sides. This would give us 3 times the absolute value of x less than or equal to 9. Now let's divide both sides by 3. This would leave us with the absolute value of x is less than or equal to 3. Now we've isolated the absolute value of x. The next step is to check the value of a. Remember, if a is less than 0, in other words, if a is negative, then the inequality has no solution. Let's look back at our problem. We have x is less than or equal to 3, so that value of a is 3. 3 is positive, so we know that this will have a solution. The third step is to rewrite the absolute value inequality as a compound inequality. This is where we use the definitions. If the absolute value of x is less than or equal to a, then we'll rewrite as the compound inequality x is both greater than or equal to negative a and less than or equal to positive a. If we have absolute value of x is strictly less than a, then we would rewrite that as the compound inequality x is greater than negative a and x is less than positive a. Let's go back to our problem. We have absolute value of x is less than or equal to 3. In inequality form, this would be x is greater than or equal to negative 3 and less than or equal to 3. So it's in between negative 3 and 3. The fourth step would be to solve the compound inequality. You would work from the middle outward to isolate x. In our inequality, x is already isolated in the middle. So this fourth step does not apply to this problem or the rest of the problems in this video. Step 5 is to graph the solution set on a number line and write it using interval notation. Let's graph the solution set on a number line first. Here's my number line. For the inequalities here, we will use a solid dot on negative 3 and 3. This represents that both negative 3 and 3 are included in the solution set, and we will shade everything in between negative 3 and 3 to represent x is in between negative 3 and 3. Using interval notation, we would write this as the interval from negative 3 to 3 with square brackets on negative 3 and 3 to represent those endpoints are included. 3 different ways to represent the same solution for this problem. We have it in inequality form, graph form, and interval form. Remember that the inequalities with the equal bar below use solid dots on the number line and square brackets in interval notation. Let's take a look at a couple more examples. Let's solve the problem 2 times the absolute value of x minus 10 is less than 6. The first thing we need to do is isolate the absolute value of x. So I'll need to add 10 to both sides. This gives me 2 times the absolute value of x is less than 16. I'll divide both sides by 2, and I get absolute value of x is less than 8. Since 8 is a positive number, we know that this absolute value inequality will have a solution. In inequality form, this would be x is greater than negative 8 and x is less than 8. So x is between negative 8 and 8, although here, since we have strict inequalities, we are not including those endpoints. Now let's graph this on a number line. Since we're using strict inequalities on this problem, we'll use open dots on the endpoint. So we'll have an open dot at negative 8 and an open dot at positive 8. Our solution set is everything in between negative 8 and 8, but those endpoints are excluded because of the strict inequality. In interval notation, we would write this as the interval from negative 8 to 8 with round parentheses representing that negative 8 and 8 are excluded from the solution set. And finally, let's take a look at the problem 7 times the absolute value of x plus 25 is less than or equal to 11. The first thing we need to do is isolate the absolute value of x. Let's start by subtracting 25 to both sides. This gives us 7 times the absolute value of x is less than or equal to negative 14. Dividing both sides by 7, we end up with absolute value of x is less than or equal to -2. In this case, we have absolute value of x is less than or equal to a negative number. Since this is impossible because absolute value can never be negative, this inequality has no solution. That's it for this video. Thanks for watching.